Okay, so this is a pretty short video on the concept of intermolecular forces. And really what we want to distinguish in this video is the difference between an intermolecular force, intramolecular force, and then we're going to focus on the intermolecular forces. So intramolecular forces are those forces between atoms. So an intramolecular force is typically considered to be a chemical bond. And so a chemical bond is, of course, covalent, ionic, or metallic. And we've drawn lots of covalent bonds. So we have something like a carbon-hydrogen covalent bond that then is intramolecular. Intermolecular force, on the other hand, then is an electrostatic force. So it's still a positive negative, but it's an electrostatic force of attraction between molecules. That's the really important distinction. Between molecules. So we are not talking about the CH covalent. We're talking about something like, say we have HCl and another HCl. This is going to be delta negative. That's going to be delta positive. And that is my intermolecular force. So we're going to look at these a little more closely. First of all, what happens when you break an intramolecular force? What is it that happens when the chemical bond is broken? Well, why don't we have a quick look?
Clearly.
Mine are much better.
Okay, it's going to go in a sec.
They have meters. I know. And they're not shears.
Oh,
They're smaller.
that was so.
So as you can see, when an intramolecular force is broken, a reaction occurs. That's a pretty spectacular reaction, the thermite reaction. And so bonds break and reform, and we get a different chemical compound. And that's what's important. So that's a reaction. We take something, however we do carry out the reaction, but we get a different chemical compound as a net result. And in thermite reaction, we actually take aluminum solid and we mix it with iron 2 oxide solid, add a bit of heat, and we get aluminum oxide. It's also solid, and solid iron. And so we have different products, so that's a chemical reaction. Well, what happens when an intermolecular force is broken? Well, I can show you this one too. Not nearly as spectacular, but we change the state of the compound. And so in that particular little clip that I carried out on my stove, we went from the solid phase to the liquid phase to the gaseous phase, but it was always water. So we did not change the chemistry. We did not produce a different compound in that process. So intermolecular forces are then those forces that keep water as a solid. And if we add enough energy, we get water to enter the liquid state, and so on. So 3 different types of intermolecular forces you should be familiar with. Unfortunately, 2 of them are known correctly as van der Waals. Luckily, we have a common name for these. So van der Waals is one type, and one of the types of van der Waals is a London dispersion force, shortened to LDFs, thankfully. The second type of van der Waals is a dipole-dipole force. And finally, the last type of intermolecular force is the hydrogen bond. And we can order these in terms of strength. And again, you may be familiar with it. London dispersion forces are the weakest. Intermolecular force. And dipole-dipole are stronger than London dispersion forces, but they are weaker than hydrogen bonds. So hydrogen bonds are considered to be the strongest intermolecular force. So van der Waals first. So as I mentioned, weak force of attraction, and proportional to the size or molecular mass of the atom. And so basically what we're looking at here is, think about this as due to increased electrons. Because as you'll see in a second, it is really the uneven distribution of electrons that gives rise to these weak forces. And so we do have to consider the number of electrons. And so if it's a larger mass, that does mean more electrons. So you can relate strength of London dispersion force to the size of the molecule. Smaller the molecule, the weaker the dispersion forces it would exhibit. So, as I mentioned, it's sort of due to the uneven distribution. If I look at this particular atom, I would say that's an even distribution of electrons. One on each side. There is no difference, there's no change, there's no polarity or no polarization for that particular atom. However, I can polarize the atom by seeing the electrons distributed in an uneven fashion. So that's uneven. And so if I look at that particular atom now, there's 2 electrons on one side, there's none on the other. That would mean this left-hand side of the atom is going to be negatively charged in essence, meaning on the other side it's going to be positive. And so that gives rise to what is known as an instantaneous dipole. And so this instantaneous dipole is charged. There is a weak dipole, one side negative, one side positive. Well, if it's a dipole, what it means is it can actually interact with another dipole, or it can actually induce a dipole. It can cause another atom to become a dipole. And if that happens, what you get is this weak force of attraction. And so that is an LDF. So what we have here is an instantaneous dipole. It may have induced this atom to become a dipole. And if it induced that dipole, now we have a positive negative electrostatic force of attraction. And so that's in essence how a London dispersion force gets established. A little simpler to look at van der Waals forces, or dipole-dipole forces are. So they're a little stronger than LBFs for sure, and they're caused by the presence of a permanent dipole in a molecule. And let me explain what that is. So what I have down here is a molecule where the delta En is low. So 0 to say about 0.4 if you remember for electronegativities. So that means there's no dipole. So that's a non-polar molecule. Well, in this molecule I have 2 different atoms, and the dark shaded area indicates that this is negatively charged. And the more lightly shaded area means this is positively charged. In essence, the molecule or the atom on the left will have a greater electronegativity. So there's a larger difference in electronegativity, and this molecule or this atom is preferentially attracting those electrons. And so as soon as we have so that's known as a permanent dipole. And so as soon as we have a permanent dipole, we have molecules that are capable of establishing dipole-dipole forces. And so that's exactly what's going to happen. Again, a weak force, it's stronger than dispersion forces, but it can be strong or weak. But again, this is a electrostatic force of attraction, so dipole-dipole force. between two polar molecules. And so again, they can vary in strength due to the type of polar bond. So a greater delta En will give rise to a stronger dipole-dipole force. But again, that's a pretty straightforward electrostatic force. And the last one we want to look at then is hydrogen bonding. And so hydrogen bonding is the strongest intermolecular force, and it's caused by the presence of, again, a permanent dipole in a molecule due to the bonding of hydrogen to either nitrogen, oxygen, or fluorine. So I call this hydrogen bonded to NOF, and that helps me to remember it. And again, if we look at this particular, we have an oxygen hydrogen bond here, and so that's going to be a polar bond. And that is a large difference in electronegativity between oxygen and hydrogen. So that's a strong polar bond, strong dipole. And so again, what we get is this intermolecular force between these two areas of a molecule, and that intermolecular force is a hydrogen bond. And it is a strong intermolecular force of attraction. It's the strongest of the three. We'll start looking at these different types of intermolecular forces and how they affect the physical properties of different molecules. And we're going to look at that based on the polarity of the molecule and the geometry of the molecule, because that's going to have a bearing on whether a molecule has certain physical properties or not.